Okay, any ideas of why for magnesium, why is there such a huge jump in energy when I start trying to pull off the third one? What is it about magnesium that makes it jump so big right there? Yeah, it's that one. Thank you. Any ideas? Maddie, what do you see?
Are the first two the valence electrons and then the third one is like the core?
Yeah, so look at magnesium here, right? So if magnesium loses one, it's now like sodium. If it loses a second one, it's now like neon, which is its goal. So it's not going to let you take off another one. This is like, you know, we talked about how the back row are my valence. So somebody comes and steals Sierra, somebody steals Kim. Sorry, we're okay letting you guys go. This sounds bad because now we're perfect. I picked them because they'll forgive me. Okay, but then it's like somebody tries to come steal Hayden now because she's my core electron, and that's not going to happen. Okay, so think in your head, don't say it out loud. So for aluminum, where would the jump be? Where would you see a big spike in energy? So just think to yourself, don't say it out loud, but for aluminum, where would a big spike in energy be if this is what we're looking at? Think kind of on our warm-up when we figure out how many valence electrons aluminum has. Okay, and then what I want you to do is I want you to show me on your fingers where the big jump would be. Would it be the first, second, third, fourth? Where do you think? If you have an idea, show me. If you don't have an idea, don't show me. So where would the big jump in energy be? Good. If you're showing me 4, you are correct. So Jasmine, help us out. Why is it 4? Yeah, aluminum has 3 valence electrons. Now look how crazy this jump is. So we have 577 kilojoules, so that's the payment I have to make to get the electron. Okay? Keeps going up. But then to get that 4th one off, huge jump in energy. So we're always going to see a spike in ionization energy when we start ripping off core. All right, our next trend that we're getting to is ionic radius. So we've done atomic radius, ionization energy, and now it's ionic radius. So this is what happens to the size of an atom when we add or remove electrons. So first off, let's review with cations. Right, that cations happen when an electron is added to an atom. Okay? Remember, you can think about it as the cat ion, the T in it is like a plus sign, so they're always positive. Or that cats have positive. Get it, right? Okay, so this is sodium. Why does sodium get so much smaller when it removes one electron?
Because that one electron's on a new level, and so when you take that away, it takes it with you.
Very good. So sodium, if you look here, thanks Ethan, sodium right now has 3 rings. If I remove one electron, it's now like neon, and how many rings does that have?
2.
Just 2, right? So we see actually quite a drastic change because in a sense it has shed its outer level. And so it decreases in size, okay? Versus if it's an anion, anions are created by gaining electrons, and what we see is it actually gets bigger. So let's say here, 1, 2, 3, 4, 5, 6, 7. Okay, from Mitchell to Dustin, okay, you guys are my 7 valence electrons for chlorine, okay? So imagine them in a circle. They're playing Ring Around the Rosies together. Except they're all negative electrons, so they don't want to touch each other. So they're like touching pinkies and as far away as they can. Okay? If Brooklyn, she's my 8th valence electron I'm adding, wants to join the circle, what has to happen to the size of the ring? It has to get bigger to fit her in there, and since they don't want to be by each other, it actually gets quite a bit bigger. But notice, is it that I added a new ring? No, I just expanded the one I had. So just be careful with that with cations, they're shedding their shell. With anions, we're expanding it. Okay? So So with that being said now, don't say it out loud. Grab your periodic table, and for a smiley face, answer this question for me. Good. So the answer is B. S2 minus is going to be bigger. All right, next trend, everybody. Okay, focus back up front. Distraction should be away. Okay, so we have atomic radius, ionization, ionic radius, and now we have what's known as electron affinity. Okay, electron affinity is the energy that gets released when an electron is added to an atom. Okay, so notice the equation here. The electron is going in because it's on the reactant side, and then the energy is coming out in result. So the way I think about this is the reason why an atom would release energy when it gains an electron is because it's getting to a more stable state. And if it's more stable, it can release the energy it doesn't need anymore. In a sense, you can kind of look at it as the energy that's coming out is a sign that the atom is happy you gave it an electron. So the more energy that gets released, the happier it is you gave it. If it doesn't really want the electron in the first place, is it going to release energy? No, because it doesn't want the electron, right? So with this trend, notice a comparison to ionization energy. Ionization energy was the energy it takes to remove an electron. So they kind of look a little bit opposite, where energy is in and an electron is getting pulled out. Right? So notice the connection here between electron affinity versus ionization energy. As I go across a period or a row, generally we see ionization energy is increasing, and also is electron affinity. So electron affinity is getting greater as I go to the right. We also see a trend that as I go up a group, it's getting bigger as well. So diagonally, if you want to think it, it's going generally like this. And a lot of our trends do the same thing.
That is very helpful.
Yeah. Except notice, what does it say? Where does the trend stop on this case?
Group 17.
Group 17. So why do our noble gases not have electron affinities at all?
Because they're all filled.
Yeah, they don't want you to give them another electron. So there's this kind of, it drops off. Right? So notice that this trend ends at group 17. The noble gases just don't have one. Okay? Then our pattern, like we said, is it's increasing as we go up in the top of a group. So there's the trend. Now let's understand the why. Okay? So let's start with a group. So why would it, let's look at the halogens, okay? So why would fluorine have a greater electron affinity than iodine? What would be the cause there? Jeff, what do you think? Okay, so it's higher up, so what's the difference there in it being higher up?
So it's smaller.
So then it makes it smaller, right? So we have this combination of, since it's up at the top, fluorine is very small, so the attraction between it and its nucleus is very great. So when you give it that electron, it releases a lot of energy.
Okay.
Versus iodine, it already has a lot of stable rings to balance itself. Yes, it wants that 8 one still, right? It's still really big, right? Look, notice the circles. Iodine's still very big in comparison, but in relation to a group, it's not as much. Okay, so what we see is that the fewer energy levels something has, the smaller the radius, and the greater the attractive force. So the fewer energy levels gives us a smaller radius and a greater force. So once again, notice the general connection that up and down always goes back to the size because it changes drastically. But then going across, why would, let's say fluorine again, why is fluorine going to have a higher electron affinity than boron?
Because it wants it more.
It wants it more, right? It's 1 away from being 8. right? Its attractive force is really, really strong. Boron, yes, it wants to get there eventually, but since fluorine is so close, we see that greater attractive force. Okay, so the increased number of valence gives us a greater attractive force in the end. And that's what we get for electron affinity. And then once again, side note, the noble gases don't have it because they don't want any more electrons to begin with. All right, next trend. Oh, first off, so notice even though, and Ethan kind of pointed this out, even though the definitions are opposite, the trends are identical. Fluorine has the highest electron affinity, and it also has the highest ionization energy. Because, here's kind of a good way to think about it, is the more an atom wants to gain an electron, the more resistant it is to losing the ones it has. Right? Fluorine's not going to give up any of its 7 because it's so close to getting just that 1 more to 8. So we see that the trends are identical even though we're talking about 2 different processes. Yeah?
So like chlorine, it gives more energy released because it wants it more, like because it just needs 1 more electron?
In terms of like what?
So the EA is electron efficiency, that's the energy released.
So that's the energy released when I give chlorine its 8th.
And so that's more than if you gave phosphorus?
Yes. Mm-hmm.
Why? Because phosphorus gets more, so
if it gets another one, it's not
released.
So phosphorus gains 1 more. It's getting closer to stable, right? But the more stable something becomes, the more it can release it.
Oh, okay.
Does that make sense? So since chlorine becomes almost totally stable, it can get rid of all that energy. Yeah, good question. Okay, so we're going to have to go old school a little bit. So on the bottom of, there's not tons, just like 2 slides. On the bottom of this, where it's blank, write in that definition. Okay?
Oh, you didn't get that.
This is the one we handed out. Yep. So write down electronegativity. Yeah, I really don't know. Like 3 slides just aren't on your notes. So electronegativity, big long word there. Okay, but what it is the attraction of an atom for electrons shared in a bond. Okay, the attraction of an atom for electrons shared in a bond. And that shared word is kind of key here. So after you write that definition down, we're going to draw a picture underneath to show what electronegativity looks like inside an atom. The picture is not technical, so don't freak out, all of you who are like, I'm not an artist. Me neither. Okay, so what I want you to draw is we're going to draw an atom. Okay, it can be simple. So like here's my nucleus. Okay, I'm going to get hydrogen. Okay. Here's like our rings. Okay, I'm not being technical. It doesn't have to be hydrogen. We're just saying it's an atom. Is write down the trend. Okay, so underneath your definition and picture, write down the trend of what electronegativity is. Okay? And maybe as you're writing the trend down, some of you may notice that it looks very familiar again. It is almost the identical slide to the one before, right? Same as electron affinity. That the trend is, as I go across, it increases, and as I go up, it also increases. Okay, so write this underneath your definition. So one way that I often think about electronegativity, and we'll talk about it as we get into other units, is the way I think of electronegativity a lot of times is it's like a tug-of-war, okay? Where 2 atoms are bonded, they're sharing their electrons because it gives them both their 8, but that doesn't mean they share equally all the time. Okay, for example, let's say if me and Aubrey are a bonded atom, and this marker is our valence electrons. Okay, so hold on to the marker. Okay, if I have a higher electronegativity, then I get more of the marker than she does. She gets it every once in a while, but I get it more.
It's like sharing a car with your sister.
Yeah. There you go. Yeah, kind of that idea. If our electronegativities are equal, then it's equal sharing. And to be honest, if the electronegativity is so much stronger, then it ends up not being shared at all, and I just get it all. Right? So that's the way I think about electronegativity. Yeah, Amy.
What's with this group 17 that they like keep saying? Like, what is
Noble
that?
gases.
So, yeah, that's a good point.
That's noble gases.
Yeah, well, so group 18 are the noble gases. So why don't the noble gases have electronegativity?
Because they're
already.
Do they bond anyways? Yeah, they don't bond. They're already full, so they don't share. So they don't have electronegativity. But yeah, good observation, Amy.
What about those two? All the way to the
Ooh, good catch there, Brady. So notice, this is really interesting, everyone. Focus back up front. So, yes, the noble gases are stable, but some of our larger noble gases, krypton and xenon, do actually bond to some things. And we'll talk about, later on, why they would bond even though they already have their 8. So yeah, notice that it's really, so this is the last thing I want you to write down underneath, is write down this right here. Okay, that the top 3 noble gases do not have electron affinities because they don't bond. And if thing doesn't bond, then it doesn't have an electronegativity. So just write that down underneath your trend. So our top 3 noble gases don't have electronegativity values. Yeah, Ethan.
So is this why if you have just hydrogen gas, so 2 hydrogen molecules, they're hard to get apart?
That's a part of it, yes.
Part of it?
Yes,
Okay.
Because they're sharing their electrons, they're both perfect. And so, yeah.
Okay.
No, that's a big part of it for sure. So on this chart right here, so this shows us electronegativity. Something to be aware with electronegativity is it's not a directly measured value. So like before, it was like kilojoules, which is something you measure in the lab. This is simply a value that has been assigned to the atoms, determined through experimental results. So when we say the electronegativity values, it's just 3. It's just 4. It doesn't have like a unit associated with it. Okay? So looking at this chart, can you guys tell me which atom on the periodic table will win every tug of war it's in? Good, Jillian. So fluorine is the buffest atom on the whole table.
Yes.
It always wins the tug of war. And who would always lose?
Fluorine is the Chris of
francium.
Yeah, so francium, to be honest, probably just gives up and just says, here you go, you can have my electron. Back up front here. Okay, so this goes back to our demonstrations we did last time. So reactivity is the tendency of a substance to undergo a chemical reaction. The whole reason why things react is because they're trying to get that stable full octet. And the more it wants that octet, the more it's going to react. Often, the closer it is to being perfect, the crazier it makes it. Versus the ones that are in the middle, yes, they want to get 8, but they're a little more chill about it. Right? You can think of it as it's like they're at the end of the race. Right? They have 7 and they just need 8. So they're sprinting to the finish. When, some of the ones in the middle, they still have a ways to go. So they're not gonna. So notice this. This is an interesting thing. So our 2 most reactive families are the alkali family, which you saw last time in our demo, and the halogen family. Because they're both one away from being perfect. Right? The halogens, what do they need? Yeah, they just need to gain 1. The alkalis, what do they need? Yeah. So with reactivity, it's kind of cool to think of. Like, imagine cutting out the periodic table and then wrapping it around.
Okay.
Right? Because the alkali metals are just as close to the noble gases are as these ones are too. Right? And we see that they're the most reactive of all the elements because of that. So let's look at the metals for the first part. So this is like our alkali metal family. So metals are on the side of, I want to give away the electrons I have. because it's closer, it's easier for me to give them away than try to find a lot more. Okay, and it all goes back to they have very low ionization energies. It's not hard, or it's not as hard to pull off their electrons as it is for something else. Okay, so on the metal side, what did we see last time? Did they get more reactive going down or going up? Which way did it go when we watched our videos and things? Which ones were the most reactive? Going down, right? Remember we had to watch videos of these ones because we can't do them in real life?
And so the lower the ionization.
So then what's interesting is on the other side of things, the nonmetals are opposite. The nonmetals want to gain electrons, and in a result they have a really high electron affinity. Or you could also think of it as they want to keep the electrons they have because they have such high ionization energies. So we get this interesting trend with reactivity where it's not exactly just one way or the other way. We kind of get a double-headed arrow of a sort when we look at it. Because metals really want to lose, nonmetals really want to gain. So where would you predict would be the least reactive elements in general on the table?
Metalloids.
Somewhere in the middle, right? In those middle groups, those ones are not super reactive.
So like,
Right? Yeah.
those are the least reactive and
Mhm. Yeah, is that what you're going to ask? So on that periodic table on your paper, draw in this two-headed arrow. Where we see down here are the most reactive metals. And then up here are the most reactive nonmetals. We see it increases kind of in both directions. And then once again, in the end, our good old noble gases just don't react for the most part. Any questions with reactivity?